Recording is rolling. It is Friday, January 24th. You guys know yesterday you guys collected a bunch of data for this pendulum lab. And today I'm going to help you guys put together the graphs. We're going to do 4 graphs. And then here's our goal. We're headed towards trying to piece together an equation so we can figure out what's the physics that's governing the motion of a pendulum. How much time does it take to swing back and forth? Okay. We have these candidate independent variables. You guys were testing, well, if I change out the mass, how does that affect the time period? If I change out the starting angle from the vertical to measure the protractor, how does that affect it? And then the length of the pendulum, okay, how does that affect it? And so we got these 3 experiments you guys did. So 1 independent variable at a time, some controls, you're relating that everything to the time period. Okay. And so put that together. Before I get rolling too far on that, a couple other things. You guys remember, I showed you guys this the other day. There's this STEM Career Showcase coming up Thursday, January 30th at 6 o'clock p.m. in the cafeteria. So I did scan this morning and put this on Google Classroom if you want to get a better, closer look at that. Also, yesterday on your desks, I gave you guys your spring thumbnail notes. Right, so there's a bunch of pages in here. This was for you guys, so you're supposed to pick this up and take it home. This is for you guys. You guys can take it. Not everybody did. So if you didn't get one, then there should be some on your desktop, so you can pick up one today. If you didn't get one yesterday. All right. All right. So let's figure this out. All right. Oh, and then we should have a few minutes at the end of class. So I'll show you guys some Blackburn pendulums, which are pretty cool too. All right. So we're doing a simple pendulum here. So see if all the mass is, see the bottom and the end, and the string has negligible mass, swings back and forth. How much time? Okay. So let's start with the you know what? Actually, let me go fill in some columns here. Okay. So I definitely need a column for time, right? Like time in seconds. Okay. Now, what I was really prompting you guys to do here, maybe I'll ask you guys: should I time 1 oscillation, or should I time several oscillations and divide by the number of oscillations? Yeah, the second thing I said. Okay. So maybe, for example, if I did 10 oscillations, some number of seconds, and then divided it by 10, I could get the time period for 1 oscillation. Okay. And why is that better again? Why is that a better method?
It's like more of an average and like after the error.
Yeah, also divides the error out. So whatever error you had in starting, stop, and stopwatch also gets divided by, if I did 10 oscillations, gets divided by 10. Okay. You didn't have to, you could do it on 5. Okay. You know what, Dave? I still have a couple other blank columns. I saw some students yesterday put gravity field in the column. That could be a reasonable thing to do, right? Because that actually is part of the equation. We were doing a little bit of thought experiment to say, hey, what if I take this up to the moon? And on the moon, I bet this would be going like really slow on the moon, right? So now we can't really test for that in this class, but maybe that could be a consideration you could have, right? And here's something you guys are going to see by the end of class today. I'm going to square one of these, or I'm going to square the times. Same way in square seconds. An alternative to that is you could take the square root of one of these variables, and you guys can see which one by the end. Okay. So that'll show up at the end. All right. So let's start with how about mass and time? Math and time. I had you guys hypothesize each one of these yesterday. So as you increase the mass, go from these small masses to the bigger mass, right? How does that affect the time period? You guys came up with some hypotheses. We're about to find out the answer. Right, so you guys ready to make some graphs on the back? Graphs on the back? Okay. Now I'm going to make some really big graphs because this shows up better on the dot cam, but you guys can use those quarter-page graphs if you like. Okay. So first graph we're doing is time period versus mass. So I put time period, vertical axis, dependent type variable, mass on the horizontal, the independent. All right, who has some good data? Who wants to share some good data?
I would love to share my data, Mr. Griffin.
Yeah. All right, Aiden, what was the largest mass you used?
The largest mass we used was 0.1 kilograms.
0.1 kilograms? All right, so put mass in kilograms, 8 kilograms.
Right.
And let's take this up to 0.1. So if now the largest mass was 0.1? Right.
Yes.
Right. So 0.10 kilograms. So
it's sorry, it was 0.2. I'm sorry.
Oh, 0.2? All right, read it.
I apologize.
Easy fix. All right.
He doesn't represent our group.
Kilograms? Outcasted. Right, 0.1. This could be 0.05. This could be 0.15. Right? And you guys know in this class, graphs always start at 0, 0. That's generally good practice. Right? Right. So start 0, scale it up. All right. What was your longest time period?
our longest time period was
1.83 seconds.
1.83. So go 0, 1, 2. So 0, 1, 2. There was some 0.5s here. 0.5, 1.5. All right. That should contain all the data points. Let's get some data points. What's one data point?
Then our next week, or our smallest one was 0.01.
0.01.
And that had 1.76.
1.76. Bam. Right there. So 0.01 kilograms, 1.76 seconds. All right, point on the board. All right, what's your next coordinate?
0.02, and I also had 1.76.
Ooh, good time. So 0.02 kilograms, also 1.76 seconds. All right, next coordinate.
And then we had 0.05, and that was 1.77. So
Ooh,
slight difference.
all right. So 0.05 kg and 1.77 seconds. All right, next one.
Then we have 0.1 kilograms, and that what 1.82.
1.82. 0.1 kg, 1.82 seconds. All right, next one.
And then we had 0.2, and that was 1.83.
0.83. Ooh, get that. All right, and that's all the points right there. 5 points. All right. So, guys, what do you think the trend is? Constant, constant, right? Which really means no relationship between those two variables,
mass
right?
don't do a thing.
Yeah, exactly. Yeah, mass doesn't do a thing. Right? It doesn't matter if it's a small mass or a big mass, as long as all the mass is concentrated in the bob and the string is negligible mass by comparison. Yeah, then yeah, mass doesn't really matter at all, right? And you might have hypothesized this yesterday before you even got any data, because you know what this kind of reminds me of is going back to the Galileo experiment. You guys remember Galileo dropped this and this off the Leaning Tower? And I got them to this day. And they fell together. So the physics one explanation goes kind of like this. Larger objects might have more weight, but they also have more inertia. And those two effects cancel out because there's a direct relationship between right, mass and force, right? Mass and weight. So if you just attach that to a pendulum, swing back and forth, yeah, it's sort of the same principle, isn't it? Right? Now, having done this lab year after year after so many years, usually this graph, and actually you guys is a little bit too, does usually bend up a tiny, tiny bit. Like it's not exactly flat. It has a tiny upslope to it, which I was kind of expecting. Why do you guys think that this graph usually has a tiny bit of an upslope to it? And that would actually kind of make sense.
Because air? No.
Ooh, that's an interesting. I wasn't thinking about that, but yeah, that is true. That is one of the simplifying assumptions. I never mentioned that, but we are sort of ignoring air drag, right? Right. That might have a tiny bit of an effect actually on the motion of the pendulum. Yeah. Right. How about this? If I attach this to a string and I unhook it and hook this one on, right? And I'm measuring the length of the pendulum relative to a pivot point up here. Right? Do you guys see from the pivot point down to the center of mass of this weight? And then if I hook this one on from the center mass, or from the pivot point to the center mass of this one's going to be effectively a tiny, tiny bit longer, maybe like a half centimeter longer, something like that, because the larger lab weights are physically larger. Right? So we're actually getting a little bit of a length effect. So that's to say maybe the length of the pendulum was not perfectly controlled. Right? And that's bleeding over a little bit into this graph, and that's why it's not perfectly flat. It's actually a little bit a tiny bit. Right? Here's good. Right. But this one, yeah, pretty nice. So by the time we get to this master equation at the end, how does mass show up as a variable in this equation? It doesn't. Yeah, mass doesn't even show up here at all. Right. All right, so one variable down, and Next wants to go. Are you guys ready for angle? Let's go into angle. So you guys were measuring with the protractor. What if I pull this at 5 degrees or 10 degrees from the horizontal, or sorry, from the vertical? Right. And so I'm going to set some axes here. Let's do a time period as a function of angle. Got a time period in seconds. Bet you guys probably measured angle in degrees. Okay. All right. How about Human? Do you have some good data for this one? Human? Maybe? No?
We did.
Yeah. How about Carson? You got some good?
I got
Yes. All right. What was the biggest angle you used?
the long, like the high, like the biggest angle.
Yeah, biggest angle.
Wait, were you talking about like distance to 90 or distance to 180?
Okay, so I'm measuring with respect to the vertical. So if you pulled it all the way up horizontal, I'm going to call it 90 degrees. So this would be 90. This would be 0.
We did.
We did.
Then 10, 20, 30, 40, 50, 60, 70, 80, and at 90.
We did the opposite.
What did you call this angle down here? Like if it was just hanging straight down
Hanging straight down, that would have been that would have been
on your lab table?
90.
Okay. So can you just very simply subtract 90
Yeah.
from, do that. So
Absolutely.
you guys got a calculator? So whatever numbers are on your lab table, just go ahead and subtract 90, and then that would correspond to what we're doing here. All right. So your biggest angle, if you subtract that out, then to orient it to this picture, right? Then now,
We did 10.
what's the biggest angle?
40 or 50.
50 degrees? All right. All right. So now I know how to scale this up. Let's go 10, 20, 30, 40. All right, so 0, 10, 20, 30, 40, 50. All right. And what was your longest time period?
Longest time period was 1.85 seconds.
1.5? Okay, so 0, 1, 2. So 0, 1, 2. 0.5 and 1.5. Okay. All right, let's get some coordinates. So what's one coordinate going to be on this graph?
40 degrees.
40 degrees. And what?
1.82 seconds.
1.82. 40.82. Right about there. So 40 degrees, 1.82 seconds. All right, what's the next coordinate?
30 degrees.
30 degrees.
And 1.81 seconds.
1.81 seconds.
Yellow.
What else you got?
50 degrees.
50 and
1.85 seconds.
1.5.
Mm. 20 degrees.
20 degrees.
1.83 seconds.
0.83. Okay, it's like up here. Right?
Then 10 degrees
10 degrees.
with 1.7 seconds.
1.7. Okay. All right. What do you guys think the trend line is for that one?
That's pretty confident.
Yeah, also constant, which also means no relationship again, right? No relationship. Okay. So yeah, it looks like it doesn't matter really what angle you pull the pendulum to. Maybe there's some kind of canceling effect. Like if you pull it back a little bit, right, the net force only pulls a little bit, so maybe it accelerates kind of slowly. Okay. If you pull it back a lot, it's going to swing faster. And yeah, overall, the time period, no difference at all. Right? So, yeah, and when we get to this master equation at the end, I don't think angle is going to show up in this either. Okay, so mass isn't going to show up. Angle's not going to show up. Okay. Well, we only got one other variable. Let's have you guys test. That was length. Are you guys ready for length? Ready for length? Okay. So,
want to hear my data, dog?
Yeah, go for it.
All right, what we measuring this time?
Length. What was your longest length?
Longest length was 0.8 meters.
Meters? All right, so length, meters. All right, so let's go, see, 20, 40, 50, 56. So 0, 0.2, 0.4, 0.6, 0.8. And what was your longest time period?
My longest time period was. It was 1.8.
All right, scale this 0, 1, 2. Oops. Let's get some coordinates. What's one coordinate?
One coordinate was, let's say, 0.8 and then 1.82.
All right, 0.8, 1.82. Surprise, so it's probably right about there. 0.8, 1.82. Got meters, seconds. All right, next coordinate.
And let's just say, for the sake of the argument, 0.66 and 1.6.
0.66 and 1.6.
Okay, what is this? This is like. Okay, data.
Meters, seconds. All right, next one.
Okay, Mr. Griffin, real quick, who would win in a fight, me or Aiden? Aiden, stand up.
Well, we'll leave that in the land of theory.
Look, okay.
He's asking for the other data.
Oh, yeah, sorry.
I just need data.
Not, but okay, so 0.47 and then 0.137.
Point.
0.137.
Wait, what?
Yeah,
What-
sorry.
Is it 1 point?
0.47 and then 0.137.
Is it 1.37?
No, yeah, it's 1.37. I wrote it wrong.
All right.
Oopsie daisy. It's 1.37.
He should be the one getting data.
Well, you know what?
Got meters, seconds. All right, we're on track so far. All right, what's the next one?
Okay, next one is. This is 5.
The next one is 0.35 the length and 1.17 for the time.
A lot of these are just like squibbles. I can't read this.
0.35. Sorry, say it again. 0.35 and what was that?
And 1.17.
All right, meters, seconds. All right. You have a fifth point.
Yes, and it's 0.25 for the length and 0.97 for the time.
All right, 0.25, 0.97. Got meters, seconds. All right. So this part right there.
Yeah.
Ooh, yeah, that looks pretty good. That's about what I'm looking for. Is what relationship do you guys think that is right there?
Linear.
Now here's a scenario that's popped up a few times in the past in this class. Okay, is that okay? At a glance, looks kind of linear. And then if you hold your ruler flush to those points, actually, does it look actually kind of curvy, maybe a little bit? Okay, which maybe makes it not so linear. Also, if it were linear, guys, wouldn't it extrapolate back to a huge y-intercept? And you then think, okay, logically, what would that mean? That means if you had a pendulum approaching 0 centimeters, like if it was like a millimeter long, it should have some definite time period to go back and forth. Say, would that really make any sense?
Why?
Probably not. Yeah, it should probably go through the origin type, right?
Oh, well,
Right. And put these ideas together. These points look a little curvy. It looks like it maybe logically heads towards the y-intercept. Now, scientifically, maybe you could head back to the lab and just get really short pendulums and confirm that. Okay, but here's what I'm suspecting. I suspect it's not linear. It's because if it's not linear, what's another candidate? Square root. You guys think square root? I bet this is a square root curve. It's probably like there's a nice looking square root type curve right there. Right. So here's my suspicion. I think time period is proportional to the square root of L. Now I'm saying proportion instead of equals because I believe in awesome stuff. Like I bet gravity fills part of this full equation if you want to make the full equation. Okay. Now, if that's true, can I square both sides of this proportionality and get time period squared would be proportional to the length? I mean, if one's true, the other is true, right? Okay. So this is what I gave you guys the fourth set of axes for. We're gonna make one more graph. You guys ready for one more graph? Right. Right. And oh, did I tell you guys before I started making graphs that we're gonna run into t squared? Right. Now, alternative to t squared is you could do the square root of L, and that could also lead you to the correct graph I'm looking for. Right. We're gonna do linearization. So this is also something you guys have seen in the past in this class. If I suspect this is a square root curve, and I say, okay, therefore, what's the equation? So that I could figure out what's the equation governing the motion of a pendulum. Here's a function of length, right? Then how curvy is that curve? Well, that's a really tricky question to answer. But if you linearize this, so if I graph not t versus L, but either t versus square root of L, or what I'm actually going to do with you guys is t squared versus L. If my hunch is correct, that's a square root, then that should linearize. And it's really easy to get the equation of a straight line. These two rise over run to get the slope. It's probably going to go through the origin, right? And then we can get it that way. So that's exactly what we're going to do. Right, so last graph. You guys ready for last graph right here? Right. This is going to be, I'm going to do time period squared and the unit of square seconds as a function of length in meters. Okay. One of two main ways to do this. Okay. All right, so let's sketch out. I'm going to keep the length the same. 0.2, 0.4, 0.6, 0.8 meters. So 0, 0.2, 0.4, 0.6, 0.8. That's meters. Okay. But all the times I'm going to square one at a time here. So if I take 0.97 seconds and I square that, I'm getting 0.94. Okay, so 0.25. Oh, whoops. Actually, I should start with the big one. If I square, well, that's almost 2. 2 squared is almost 4. Let's scale this. I need to scale this, right? So let's go 1, 2, 3, 4 should contain all the data. 0, 1, 2, 3, 4. And remember, this vertical axis is now pretty abstract because it's square seconds. Was that? Okay, well, something I'm going to use to make a nice looking graph, right? Okay. So over here, we got at 0.25 meters right here. I got 0.94 square seconds. So 0.25, 0.94. This is meters and square seconds. Okay, there's 1 point. Okay, next one. Okay, at 0.35 meters, 1.17 seconds. Square that. That's 1.37. So 0.35, 1.37, 1.37. I think it's right about there. So 0.35, 1.37. So that's meters and square seconds.
No, that's not what I'm talking about.
So we got next one is 1.37 second. I square that. We got 1.88. So 0.47, 1.88. 0.47, 1.88.
Really?
So right about there.
5 points per razor.
Meters, square seconds. We got 1.6 seconds. Square that. It's 2.56. So 0.66. 2.56. There's 2.5. 2.56. Probably right about there. Meter, square seconds. Okay. And then at last point, okay, 1.82 seconds. I'm going to square that time, get 3.31. That corresponds to 0.8 meters length. 0.8 meters and 3.31. Well, here's 3. It's right about there. 0.8 meters, 3.31 square seconds. All right, what we got here? Oh yeah, guys, does that look like pretty much a direct relationship? I think that's pretty good. That's oh yeah. Look at that. Find the best fit. Look at that. Aha! It does. Fits right through those points, and pretty well goes through the origin. That's exactly what I'm looking for, right? Oh, and this is put my title, T squared versus L. Okay. So yeah, this line pretty well confirms time period squared is in fact proportional to L, or if you like, time period is proportional to the square root of L. So it confirms the previous graph was a square root. Okay. Let's go to the next step. Let's get an exact equation for this. Guys, can I get an equation by finding the slope of this line, rise over run? Right? And then this goes through the origin. This should be like a y equals mx, that area. Okay. Now, really the best way to do it is pick 2 points on the line and do rise over run. Okay. Since it looks like this coordinate, the line goes right through that one, and I also got this going through the origin, I'm going to pick these 2 points right here. So let's do this rise over this run. So this rise, I got 1.88 square seconds divided by this run, 0.47 meters. Right? So here's an equation for the line. We got time period squared equals, ooh, whoa, that was coincidence. Guys, look at that. That was a weird coincidence. It comes out an integer value. So I've got 4. Now that is units, square seconds per meter. And then multiplied by the length. Is that all right? Right? Is that okay? Is that the equation of that line right there?
Yes.
Right. Now, how I framed this yesterday is I just said t equals. I suppose you just want a hard time. I just want to, what's the time? Right? Guys, how can I take this equation and just get the time? What do I do to both sides? Take the square root. Okay. Guys, what's the square root of 2? Or sorry, what's the square root of 4?
2.
Is 2. Right? And that'd be seconds per square root of meters. And then multiply by and then the square root of L. So this one right here, I'm going to box this one in, is also describes that line, which also, by the way, describes this square root curve over here. Okay, so both these equations are really telling the same story. Okay, and this one's just in terms of time. Like I said, all right, there we go. Good. All right, and then finally, let's show you guys textbook version right here because I got a poster. I've got the actual textbook answer right here for classic pendulum. Okay. Now you guys know gravity field's going to show up in the general equation. Gravity field. Okay. So remind me, should I multiply or divide sort of by the gravity field? Like here's this on Earth going back and forth. If this was on the moon, where there's very little gravity, that'd be more time period. Guys, less gravity is more time period. Is that a direct type or an inverse type relationship?
That's a direct type. JK, inverse.
Inverse, right? One variable gets big, the other gets small. More gravity is less time period. Less gravity is more time period, right? Right. So I bet I have to somehow divide by gravity field type. Okay. Here is the textbook answer. Time period is 2 pi square root L over G. Oh, look at that. Here's your time period and length relationship. Yep, there's definitely a square root type relationship there. So that's good. We're on the right track. Okay. Yeah, you definitely something to do with divide by gravity field. That's still in square root. That's okay too. Okay. Also, see, according to the textbook, I'm making the claim there's a 2 pi thrown in the mix. Oh, hey, we could test that because you guys have this empirical data. Isn't this the exact equation we came up with right here? Right. Let's see how close this is. Guys, if I do 2 pi divided by the square root of g, what should that be right there? What is 2 pi divided by the square root of g? Should it be about this number right here? Let's see. 2 pi divided by square root of, what number should I type for g? 9.8. And when I hit enter, what number should I get again?
Wait, where are you at?
Okay, guys, I just did 2 pi divided by the square root of 9.8.
Yes.
And what number should that come out to? Here, I'm making a prediction before I hit enter. 2. Right? Should this be 2?
Yes.
All right. Let's see. Let's see if you guys did a good job on this slab or not. Let's find out. What is this going to be? Yeah. It's 2. Look at that. It's 2. It's 2. Oh, yeah. Yeah, you guys did a real good job on that lab. All right, you guys got all the data? You guys got all 4 graphs? Okay, when you have all that, throw that in the grade tray. I will give you guys points, lab points. And since we got about 4 or 5 minutes here, I have a video for you guys on Blackburn Pendulum.